Thank you very much. Yes, and also thank you very much for the introduction, for my talk, and for the invitation at this wonderful place. I'm very happy to be here again. So last year I presented something about more algebraic, and this there are intersections to today's talk, but it's also a bit very different. So I'm still a PhD student at the University of Vienna and in Ria-Saclay. And so this is my third year, and I will be finishing next year, hopefully. Yes, I will present, as Gerard already said, about creative telescoping. This will be somehow the first part, and then the Canham model in genus 1, which will be the second part, where we'll somehow use the first ideas. And here I have three motivating examples, which look very different, and there are three somehow identities. But my main point here is that all three can be derived by the same method, and not only method, by actually an algorithm. And yeah, so this will be the first part somehow. So in the first case, we have the well-known a priori numbers, which were used to prove the irrationality of set of 3. And the key step was to prove that those numbers, a n, defined like this binomial sum, satisfy this second-order recurrence. The second example is connected to the previous talk and also to the next one about moments. And here I have just taken one example where we have an algebraic function and we compute this one, and we compute the moments, and it turns out that the generating function is actually a constant times a hypergeometric one. And that's actually a very interesting example because this function is algebraic, but this one is not. And anyway, and a third example is, which will be quite what I will talk about in the second part of the talk, namely about the surface area of a projection of the Clifford Taurus to R3. And it turns out that if one just writes down the integral defining the surface area, one gets this thing, and it can be simplified to this very nice looking hypergeometric function which I will define. So all of these three things can be proved by the same idea, which I show now. So here are now all the three proofs of the identities before. And I want to emphasize here that they are algorithmic. And also on this very nice quote from the paper of van der Poorten on this part. Yes, so initially this was derived by Don Zagier. And nowadays we know that there are very nice algorithms somehow generalizing the idea, which I will explain. So how to prove such thing? One can find nowadays very, very quickly, as you see, two things. One is an operator in the variable or the function or operator n, which is defined like this, so it just shifts n by 1, and a so-called certificate, which we will talk a lot today. So this rational function c, with the property that if you apply this operator to not the whole sum, but just this binomials, then you get actually this thing. So k shifts k by 1, and big N shifts n by 1, and so you get this identity, which you can very easily check. So this is just a product which you multiply out and check that this is true with these two things. But now this follows immediately, because now if you sum this identity from 0 to n, and you watch out a bit for the singularities, but this I will somehow hide a bit, then you get that the sum satisfies this recursion, just coming from the operator. So this is the sum variant. Now looking a bit differently, but actually the completely same idea. We have these moments, and we want to prove that the generating function satisfies this identity, so which actually will prove that it satisfies the differential equation. And again, a very similar command, which is now creative telescoping, called creative telescoping, but which does something very similar, computes again. So an operator L with the same shift operator n, and again a rational function with this identity, which can be very easily verified afterwards. So you take here the derivative now, not the discrete shift, but the derivative of this rational function times the initial function. turns out to be the same as this operator applied to the function. And now again, in this case, you don't sum, but you integrate in the range from 0 to 1, and you again get that this must be 0 because it will vanish at the boundaries, and therefore you get a recursion for the variables for the sequence m. So you get a differential equation. So you solve it and you find this function. So a very similar idea. And finally, what my actual protagonist of the talk is this identity. So first, in order to prove it, one will first rewrite it as an integral of a rational function, and I will explain why this is very useful. And then apply again the same command, which is creative telescoping. I will talk more about the implementation and the algorithm to the function f, which will again find an operator L, in this case a second order operator, and two rational functions which are quite big. I don't display them here, but one can look at them, and satisfying this identity. Again, as soon as you found it, you can just easily prove it. It's just multiplying out more or less and differentiating rational functions. And then again, you now integrate over a cycle, and since these are derivatives, they will vanish, and you get a differential operator which is satisfied, or which annihilates the left-hand side. You solve it and you find the right-hand side, more or less. So these three examples, which look very different, can be done by the same method. And now let me put it into a more somehow more conceptual picture. So we have these inclusions, which I will now explain. We have so-called d-finite functions, which correspond to p-recursive sequences. The definition you can see here, and I'm sure we are all familiar with. So a function is called d-finite, or power series, if it satisfies a linear differential operator, which can be written like this, or in the operator form like this. So before that, I showed hypergeometric functions, so they are just defined as follows. So we have here the Pochhammer symbol, and then as a power series, we defined a hypergeometric function like this, and it satisfies a second-order linear differential equation, as we all know. And as I already mentioned, they correspond to p-recursive sequences, so these are sequences that satisfy linear recurrence relations, which can be rewritten as in operator form. And here is the recursion for the coefficients of the hypergeometric function, which is now first order. A subclass of the d-finite functions is the class of so-called period functions, which are a very interesting hot topic. And they can be roughly defined as follows. So you take some rational function in t and some variables x, which you will integrate out on the semi-algebraic set. So these are defined very analogously to these periods numbers, but now with a parameter t, so these are functions. And so here is an example. So, for example, this is the example of the perimeter of an ellipse computed by Euler already. So it is defined, or one can define it as an integral of an algebraic function, which is equivalently to be an integral of some rational function. So this is a period, and indeed it satisfies this second-order linear differential equation, which is actually a hypergeometric equation. And so here are two very nice statements. One is a theorem, and the other is a conjecture about the periods and their relation to the d-finite function. So the first one, so I do not define g functions in this talk. This comment is rather about the arithmetic part of the conference for those who are interested. So theorem attributed to Katz, and with a very nice proof in the book by André, says that the period function is actually a g function. So this already implies that it is a very special d-finite function with some arithmetic properties. And actually the famous Bambieri-Dwork conjecture says that the opposite is also true, that g functions are exactly period functions. And also in my talk, diagonals will play a role, and those are special period functions, as we will see now. So a diagonal can be defined very elementary and explicitly, namely by the following. So before that, we integrated some rational function, and now we do a special kind of integration. Namely, so given a rational function in the variables x1 until xn, we expand it as a power series. And then we collect those terms which are somehow on the diagonal, saying that they have the same index. So if we expand it like this and you get some coefficients ci1 until cin, then the function t is the one that collects the coefficients ckk as its power series. And so those sequences, which come from diagonals, are already, so they have also very nice properties. They classified to be so-called multiple binomial sums, which I will also not define, but as you see in this picture, so the a Paris numbers I had before, for example, are obviously some kind of sum of binomials, so they are diagonal, and there exist explicit constructions of this rational function satisfying this. Algebraic functions are diagonals in two variables, this is known, and yeah, so all kinds of binomial expressions. And here you see, for example, the proof that this function is a diagonal. So another way to prove the last one, and this is actually the main thing for the creative telescoping theme I'm talking about, is that such diagonals can be represented first as taking the residue of the rational function, so just shifting somehow the diagonal to be vertical at the position -1. And then as soon as you represented this as a residue, you can write down an integral. Therefore, you immediately see that diagonals are special periods somehow over cycles that are vanishing, like here. And also another very interesting conjecture about this topic is this Kristall's conjecture, which says that somehow again a bit on the arithmetic side, if you now restrict the g functions to be not only this condition on the denominators, but actually to be with integer coefficients, and you also restrict them not to grow very fast, like in the g functions case, you obtain actually a diagonal. So this is widely open, and it's actually also open for these hypergeometric functions, which I've written here, and actually even for explicit examples. So, yeah. So this concludes somehow the definitions part, and now let me come to the principle of creative telescoping. And so my main point in this section is actually that creative telescoping can solve a variety of things, as we saw in the first slide. So, and the goal is, given a period function, or it will work for diagonals surely, and yeah, as we saw for special period functions as well, we want to find, like, construct the annihilating ODE. So we know that there exists one by the previous slide, but how to, so we are just given a rational function, and we want an integration cycle. And now the question is how to find the annihilating ODE. So this is the more precise statement, as I mentioned. And the idea is, like on my previous slides, the following. So by this Stokes formula, we have that derivatives are integrated to 0. And so for any rational function c. And so what we want is the following. So if we can find an operator in just a variable t and the derivative, and these functions, which will be called certificates, which are rational functions, such that this identity holds. So I recall we want to integrate the rational function, and we want to write this rational function, so some operator applied to it, as the sum of derivatives, more or less, with respect to different variables. So then this operator will be exactly the annihilating operator for the integration cycle, because the derivatives vanish after integrating. So this somehow summarizes the principle that if we can find such an operator that produces the sum of derivatives, then we will have found an operator for the integral. And another main point is that this telescoper and the certificates always exist for this case of integrating rational functions, and they can be found algorithmically and very efficiently, or quite efficiently in practice on many examples, as we'll see. So here I present one of the original works. I will talk about history of creative telescoping on the next slide, but I wanted to already now show the origin of the story, so to say, namely for integrals of rational functions, or actually even for hyperexponential functions, those are which satisfy this this identity that, or the property that the derivative divided by the function is rational. So for this class of functions, the algorithm from 1990 is this famous Almqvist-Zeilberger algorithm, which works as follows, to be quite compact. And you see it's very nicely presented. So given two, or given a function h, which we want to compute the integral of, we define a as this rational function and b as the kth derivative divided by the function itself. And then the main step of the algorithm, so we do this for k from 0 to r, and the main step is then to decide that this differential equation with parameters, for some parameters c0 of t until cr of t, admits a rational solution g. And so the main idea, or the main task in this question is how to do this, and it can be shown that this actually leads to a linear algebra problem, which can be solved for any specific r, and then the algorithm just increases r and tries to solve this for a rational function, g. And as soon as you find something like this, then you just return the differential operator which comes from this c, and with the polynomials or rational functions in t, and g is then the certificate. So this somehow solves already the problem for integrating one hyperexponential function. And so then the topic somehow exploded, and there are many, many contributions to this, which I try to summarize on this slide. So of course, this method, or the idea of integrating or differentiating under the integral sign, this was already known to many, many people, and so yeah, many are famous for this. So for example, Feynman's method of integrating is exactly this, but this works somehow on examples, and at the same time solves indefinite integration, like it was done by Hermita or Ostogradsky. The algorithmic aspect, which I just described, is more somehow different in concept. There the idea is that there exists really an algorithm that will terminate and will find a solution, always. So this is the nice part about algorithmic. And this algorithmic creative telescoping, which, as I said before, produces this differential operator and possibly certificates, can be somehow summarized in this 4 generations. So G stands for generation. And I will probably not go into much detail here, but maybe just mention that the implementation which I used for the example before, I will use, is the one by Kuchan from 2010. And this is based on rational solving, as I explained before, in the very simple case of the 1990s algorithm of parametric ODEs. And today there are more sophisticated methods, so to say, based on reduction algorithms by many people.
And are you trying to tell us that we should go after to the 5G?
Yes, if you can invent some, people will be very happy, probably. So another quite modern viewpoint on this, and this is exactly tries to summarize this 4th generation creative telescoping, is the following: is the connection to the Ramko homology, as you, I'm sure, already noticed in this whole context. And I will probably not go also too much detail on this. So the problem can be phrased as follows. So we have a function. Now I will assume that it is homogeneous. So this is the space L with the parameter t in the variables x, and also it can have some denominator of homogeneous functions of degree p. And also we are given this closed cycle gamma, which we'll integrate. And we wish to compute the differential equation satisfied by this, where f is given like that, where this function f is square free. And phrased differently, we want to find a non-trivial element in this space, because we said before that derivatives are integrated to 0, we are actually working here, and so this is the nth. So here, notice that we can restrict ourselves to homogeneous of degree minus n minus 1. So this is the nth de Rham cohomology, which we know that is finite, and more importantly is that we can use so-called generalized Griffiths-Dwork reduction to go from f to here now in square brackets f, which has this very nice property. And then as soon as you have this, what you will do is you will compute the derivatives of f minus this reduction, and then find linear relations over L. And you know that it will always terminate, and moreover, you can have very nice properties on this reduction. So summarizing this in a theorem, the first part, which I said was already proved and noticed by Griffiths, and then the algorithmic part is quite recent. So as I said, this somehow summarizes the ideas of the fourth generation. So there is a slight assumption on when this works, but this can be perturbed or modified such that it works always. So we have that this space is finitely generated, and moreover that the generalized Griffiths work reduction, which I did not explain much, but it does approximately this, can be used to compute the minimal regular telescoper. And what minimal and regular means, so minimal is clear, but regular I explain on the following slide, which one should be very careful when working with creative telescoping is this. So this example already originates from Picard, which I mentioned before. So this can happen if one is not careful with these tools, namely if one has a function f, say this one, and we want to integrate it dx, dy, dz. What actually holds in this case is that we can rewrite it as a sum of three derivatives in this explicit case. And so we have that the operator 1 times f already is the sum of three derivatives. And we would expect that this integral is 0, but it's not always, not for all cycles. And this comes from the fact that we actually introduce new singularities here. So if you have some cycle which lives in this vanishing set, so to say, this decomposition is not useful. So the conclusion is that these certificates are sometimes important. And actually, what I said before is this regular certificate, meaning that a certificate is called regular if it has no other poles than f. So actually, when we are integrated, we are interested in those kinds of certificates, because then we know for sure that this problem cannot happen. So we know that we don't introduce new singularities, so it will be 0. And therefore, this quotation from the 2013 paper, which I mentioned before, so actually, you don't need to compute the certificates if you know that they exist and that they are regular. And the nice thing about the Griffiths-Dwork reduction is that it does compute regular certificates. So it does not need to compute it, and that's the other.
Is it the case that there will always exist a regular one?
Yes.
Okay, so you can compute a non-regular one, and then you don't care because you know that there exists one. You don't need to show it.
No, you want an operator that corresponds to the regular certificate.
Yes, but you say that the existence and regularity is enough. So if you have a non-regular one, and you say that a non-regular one implies that there exists a regular one, so and if you say that the existence is enough, then we are happy. Yeah, so
so this quote is taken a bit out of context, I agree. So the certificate obviously depends on the annihilating operator. And if you found an operator and you know that it corresponds to a certificate which is regular, then this operator will be fine. Okay. So yes, so before I go to the next part, so this was my summary about creative telescoping, which I will now apply in this case of the Canham model, which goes as follows. So this is now, this part is joint work with Ali in Boston, who is one of my advisors, and Thomas Yu, and so it is about yes, the Canham model and the uniqueness of biomembranes for genus 1. Let me try to summarize shortly the framework. So we are working in the model of minimizing this so-called Willmore energy, which over oriented closed surfaces S with prescribed genus, area, and volume. So H is the mean curvature, and this is the quantity one wants to minimize because in this Canham model it says that this will be somehow the shape of the biomembranes corresponding to these parameters. Yes. So maybe I should also mention, so this model is very similar to the Helfrich model, where you also prescribe another quantity here. Yeah, so the existence of this model is studied excessively, and most notably maybe in this seminal paper of 2014, where the authors proved the existence in genus 1, for example, for some specific choices of area and volume, which I explain now. Namely, because this quantity is scaling invariant, and it's actually even more than that, it's also invariant under Möbius transformations, minimizing given the area, the surface area and the volume is equivalent actually to minimizing given the isoperimetric ratio. So this is the ratio you can compute like this, and that is by the isoperimetric inequality always between 0 and 1 if and only if this surface is a sphere. So now regarding uniqueness, there was this question for which genus G and isoperimetric ratio is the minimizer unique, so the surface unique, so to say. And this was formulated in this conjecture very recently, which I find very nice. So for the genus 0 and genus 1 case and the isoperimetric ratio in this interval, we have a unique solution, so it's a conjecture, if and only if the following. So when we have a genus 0, then the unique solution is always the surface of revolution. In the genus 1 case, we get these two distinctions. And this third part is exactly what I mentioned before, this famous or nice paper by Marquez and Neves, that if the isoperimetric ratio is between this quantity and 1, then we actually know that the unique solution, or that the solution must be a stereographic projection of the Clifford Taurus. So here I show some of the stereographic projections. So this is just the usual torus, and now, so to say, we invert this picture at a sphere which first sits exactly in the middle, and then we move the sphere to the left. So this is how these images are produced, and the statement is that if you prescribe the isoperimetric ratio, then it is one of these pictures. And so the conjecture is that it is also unique in that case. And also in the case, so the reason for this tau is that as soon as you reach this part, you minimize somehow the isoperimetric ratio for this case. And if you go below with the condition, then you will have some, you must have some other solutions, which is not clear, but in experiments one gets it. And so the theorem, which is very recent, is the following. So the shape of this projection of the Clifford Taurus to R3 is uniquely determined by the Clifford ratio. So by the isoperimetric ratio. So in other words, if you each of these pictures has a different isoperimetric ratio. And given this statement, it is now clear that this third part holds, because we already know that it must be a projection of the Clifford Taurus. And if it is uniquely given by the isoperimetric ratio, then it must be unique. And now I want to say a few words about the proof of this theorem. So it is mostly by Yu and Chen, and but with some condition in the statement, which was in the same year actually proven by Melzner and Metzaroba with some analytic techniques, and by Boston and myself with some very different techniques, which will be somehow the combination of the two parts of my talk. So, about the Clifford Taurus, let me define it. So the Clifford Taurus is the set in R4 defined like this. So it's a subset of the sphere in R4. And the projections of it are, as I mentioned before, parameterized by the following set. So we have, we define this, where is it, I of x, y, z as the inversion map about the unit sphere centered at x, y, z. And so what Yu and Chen first prove is that this shape of the projection of the Clifford Taurus is just given by applying this map, where x is some parameter a and y and z are 0, to this Clifford Taurus. So this is the usual torus with major radius r and minor radius 1. And if you now move somehow this dot by a Möbius transformation to the left, then you obtain all possible projections of the Clifford Taurus. This is somehow the statement. And now we want to show that the Clifford, or the projection of the Clifford Taurus, is uniquely determined by its isoperimetric ratio. And it follows from these two propositions. First is that actually the surface area and the volume of this first translate or scaled and then inverted shape of the Clifford Taurus are given by these pullback of hypergeometric functions. So this is somehow the first statement, and the second is that if you now compute the isoperimetric ratio, or the square of it, which is just defined like this, so you take the volume squared and the area cubed, then this function is increasing with t. So in other words, if you now pull this point to the left, you obtain a value which is more or 1, so this approximates the sphere, but monotonically. And this already so these two things prove that the isoperimetric ratio uniquely determines which one of these pictures you're in. And now in the remaining few minutes I will explain the proof. So I said the most important thing, so I can now relax. So show you the proof goes as follows. So we have the triple integral, so I will show the proof only for the volume. That's the first. And the volume can be just computed similarly to my first slide by this triple integral of some function defined like this. So there are sine and cosine, and first we do this transformation, obtaining a rational function in x, y, this small radius r, which we integrate from 0 to 1, big R, which is a parameter, and the variable t. And now what my statement is that this integral, so this function, is this hypergeometric function I showed before. And I just explained you the tools how to prove it. So we just apply creative telescoping and define an operator. And indeed, if we just apply this very nice implementation of Kuchan I mentioned before to this rational function, we find the operator 1 and 3 certificates, such that this is a sum of 3 derivatives. So this is exactly the problem I said before. Even though this function does not integrate to 0, we can find such a decomposition. So these 3 certificates are quite large, but one can find them and check this. And so this is useless somehow in our problem. And so the second idea is, okay, we know that this one should really work because this one is now a cycle integration. And let's do the integration dx dy first, and then integrate dr by hand, so to say. So we expect some hypergeometric function for integrating dx dy already and then integrating by hand. And indeed, in this case, if we just integrate dx dy, so we want two rational functions whose derivative with respect to x and y give some operator applied to f, we indeed can find something non-trivial. And inspecting the common denominator of C1 and C2, we find this. And then, so it is not regular, but almost in the sense, in some sense. So we find some polynomial in x and y which will not intersect our integration boundary. So this proves that this integral dx dy satisfies this differential operator L, which already looks very good. So as I said, there's intersection with gamma empty. So what I just said before is that this g, which is this function in the middle, satisfies such a second order differential operator. And from there, I will now maybe skip this part, we can easily compute the integral ds and find what I said before, some pullback hypergeometric function. So this is the first part. And now, maybe in the last 2 minutes, I guess, I will show that this function is increasing. And so, as I mentioned before, this can be already also proven using these methods of Meltzner and Metzaroba, who examined somehow the growth rate of the coefficients. But here I show a very different proof. So after, or modulo this substitution, we find this decomposition of h. So we want to, or of the function before, and so we want to prove that this h is increasing now from 0 to 1 after this substitution. And maybe, yeah, to skip some details, the main trick here is to write it as a product of two hypergeometric functions. And for the one, it is very easy, and for the other with the parameter, we can use this very nice identity that this thing, so the derivative, is also some hypergeometric function with some not so nice parameters, but there we can show that all coefficients will be positive and then it will follow. So I just skipped most of the details, but this is not so very important. So let me now come to the conclusion. And so I have 2 points in the conclusion about creative telescoping and 2 about the part after. So first I want to say that creative telescoping is a very powerful tool for dealing with period functions or diagonals. That implemented versions really exist and are very useful in practice and can solve really non-trivial problems. And my other 2 messages were that the surface area and volume of any projection of the Clifford Taurus can be expressed in terms of hypergeometric functions, and that in genus 1, one gets indeed a unique solution because of this. Yes, thank you.
Now we have some minutes for questions, and
we have just a minute to the last thing. You want to prove positivity of something, yeah, some parameters.
Yes.
But can you just compactify the domain and have in the boundary Taylor expansions and then check positivity of Taylor expansions, then you get compact domain, you can check numerically and stuff.
So indeed, one, or the original, so no, let me say it like this. So in the proof of Yu and Chen, so what their statement was that if the sequence is positive, then it follows what we want. And now it remains to show that the sequence is positive, and indeed the sequence is p-recursive. So for a p-recursive sequence, it is, you know that you know the asymptotics, you know that it will be eventually positive, but you need to show that it's always positive. And you look at the first 100 terms and you say, of course, it increases, but you need to show that it really increases, so the asymptotics when they start. And this was done by Meltzner and Metzaroba. So really rigorously proved that the asymptotics already start in the very first, so proving that the sequence terms are positive. And this approach is not ad hoc, so this is very nice. So they really have algorithms for proving positivity of p-recursive sequences.
the questions. So we thank the speaker again.
Thank you.